Alrighty, so we'll go ahead and get started. We're just a minute past 10 o'clock, which is our start time. So first off, I'd like to thank everybody for joining us today. Today we'll be presenting on the Advanced Electrolyte Model, which is developed by distinguished staff scientist Dr. Kevin Gering at Idaho National Laboratory. So we'll be going over some of our more recent software development efforts that we've been working with battery manufacturers and researchers around the globe to incorporate, their feedback and requests with a lot of these new capabilities that we'll be discussing today. So for our agenda, we organized this webinar into 4 parts with an introduction, an AEM overview, then the ACCC description and overview and introduction to that. So the ACCC module stands for arbitrarily chosen chemical compounds. And then part 4, we'll do a live software demonstration and a conclusion and a Q&A. So first off, a little bit about Ridgetop Group and Idaho National Laboratory. We've had the great pleasure of working with Kevin and I now for almost about 10 years now. And here at Ridgetop, we've been doing reliability engineering applications and developing condition-based maintenance, prognostic health management, and integrated vehicle health management solutions since the year 2000. We're also AS9100D and ISO 9001 certified facility. And in summary, we're a B2B hardware and software engineering company that develops the CBM, PHM, and reliability engineering solutions for aerospace, transportation, energy, and industrial applications. And Idaho National Laboratory, they're part of the U.S. Department of Energy's complex of national laboratories, and they are also the nation's leading research facility for nuclear energy research and development. So the problem description that we'll be kind of addressing today is the need for battery health modeling, simulation analysis software tools throughout the lithium-ion battery life cycle. And as we can see here in the chart in the upper right, there are 3 key areas circled in red that we've developed tools and solutions for in partnership with Kevin and INL. So today we'll be focused on the Advanced Electrolyte Model, but we have other tools and capabilities that support the battery manufacturing and design phase, battery first use, and battery second use applications. And our technologies and tools help address customer pain points such as decreasing the time to market for new battery designs and chemistries, and helping them optimize charge and discharge protocols for their particular system or deployment environment. Some of the other tools and capabilities within our collection of tools include the CellSage battery health and modeling software, which is a patented tool also developed by Dr. Kevin Gering at Idaho National Laboratory, and then our adaptive remaining useful life estimation software known as AROL. We also offer a number of different engineering services for hardware, firmware, and software design as it relates to battery management system, cycle life testing, or IoT and embedded systems in development for PHM applications. So here we have a short overview for the AEM software, and shortly after that, I'll turn it over to Dr. Kevin Gering from INL.
Batteries are becoming more abundant in our everyday world. They power everything from cell phones to electric vehicles to grid-scale storage for renewable energy. Battery design must be tailored to each application to optimize performance, longevity, and the product's weight. To this end, Kevin Gering, a distinguished Idaho National Laboratory scientist, created Advanced Electrolyte Model, or AEM.
AEM is a molecular-based computer simulation program for discovering and optimizing electrolyte formulations in batteries to improve battery performance.
With AEM, researchers can determine over 100 property metrics virtually. It allows changes to the profile of a battery on the molecular level without having to build a prototype. By accurately predicting the performance of complex electrolyte formulations, AEM helps developers produce an efficient battery system and reduce energy storage costs. AEM can help capture and store renewable energy from sources like wind and solar more efficiently and at varying conditions. AEM also provides time and cost-saving benefits to accelerate electric vehicle and grid-scale battery system development.
AEM provides vast possibilities with over 50 solvents and nearly 40 salts. This creates millions of combinations, enabling users to find ideal candidates for their specific needs while considering the merits of various electrolyte options.
Each AEM analysis generates more than 20 reports, covering aspects like transport, thermodynamics, physical properties, thermophysical, kinetic, molecular, and macroscale metrics. This comprehensive information empowers researchers to make well-informed decisions on battery chemistry.
AEM's extensive predicted property sets span broad ranges of composition and temperature and are crucial for understanding battery electrolyte performance. Over 100 property metrics are generated and reported with each simulation. This includes ionic transport functionalities, thermodynamic and thermophysical terms, properties tied to molecular processes at interfaces such as lithium desolvation, electrolyte permeation into electrodes, and many more. AEM significantly accelerates battery development, bringing advanced battery applications to market more quickly.
Success of AEM can be seen by its increased adoption, where several large corporations and universities have licensed AEM to help accelerate their battery programs. The Advanced Electrolyte Model, helping create a world powered by clean energy.
Next, we'll move into our second part of the webinars with a brief AEM overview and then followed by the ACCC introduction.
Okay, thank you, Wyatt. So let's just look at what is the AEM. It's a molecular-based chemical physics property prediction software tool for electrolyte solutions. So when I say chemical physics, that's analogous to statistical mechanical based physics interpretations of the system, and it's a quick calculational platform to use compared to ab initio, and I'll say just a little bit more about that later. It does provide genomic level predictions at over 100 property metrics per simulation, and these range from molecular to macro scale properties, and you'll see this in a following slide. Currently, the library has over 60 solvents and about 40 salts. Most typically, the runs take less than 10 seconds. And during this 10 seconds, the model covers thousands of conditions with regard to salt concentration and temperature and solvent formulation. If you want to optimize a given formulation, then those optimization runs will take longer, but they're still very reasonable and can be done in a matter of a few hours. The code allows highly customizable inputs, so the user can assign up to 10 solvents and 2 salts per mixture. And then wide ranges of salt concentration and temperature are also allowed. So salt concentration, generally, you can go up to about 5 or 6 molal for organic type systems, and up to around 15 molal for aqueous electrolytes. The model generally tries to maintain about plus or minus 5% average deviation from lab data. That sometimes depends on which metric you're looking at. Some metrics, their laboratory data carry with it large error bars, such as diffusivity measurements and some transference measurements may be way beyond the plus or minus 5% coming from the lab. So even so, we try to heighten our predictive capability to within plus or minus 5% of the available lab validation data. The outputs include 20 reports per run, and each report contains a distinct property category. And of course, the software distribution is handled by Ridgetop Group. Next. Okay, So the current version of AEM released this month is 2.24.2. It's compatible with all the Windows environments that you would find in any office or research group. And then the storage requirements are actually quite modest, generally less than 500 megabytes for the executable files. The report files that are generated for each run can vary in size depending on the user inputs. So in practical terms, a report file storage requirement is generally between 5 to 500 megabytes. Now, if you do optimization runs, those files per run can get bigger than that. Service is handled between INL and Ridgetop Group. So INL provides initial guidance on software usage and oversees periodic updates, such as expanded library, adding new components. Ridgetop Group facilitates the licensing and software distribution and notification of updates. Next. This slide covers the AEM outputs arranged in 7 categories. And so each category has meaning toward different types of research questions that can be answered. Starting at the top, thermodynamic properties. These some of these are found in things like Newman transport models that are very valuable for taking electrolytes and then putting them into a operating system that has electrodes and separator and electrolyte. Things like osmotic coefficients, activity coefficients, species equilibria for single ions, ion pairs, and triple ions, and vapor pressure depression. These are all very useful terms to try and describe the real physical consequences of utilizing a particular electrolyte for batteries. Next, going clockwise, the ion solvation terms are based on the molecular scale. And that's where we see things like solvated ion diameters, solvation numbers for not only just the cation, but for the anion, solvent to ion binding energies, and things like cation desolvation energies and times are handled through a ligand-wise process. And then some other terms regarding communal solvation or multidentate solvation, and then microstructure terms like solvent and salt partitioning. Permittivity is handled rigorously within the model, showing how the solution and solvent permittivity changes with the addition of salt. And then as we go around, I'll hit upon a few things here. Things like Walden analysis and osmotic pressure, surface charge effects can also be obtained through the model. And then under rheological terms, we have density and surface tension, permeation of the electrolyte through different pore dimensions. Very useful for studying the choice of electrode design and how that might impact how readily the electrolyte is able to permeate through that. Then the last 2 categories involve thermophysical properties, things like enthalpy, thermal conductivity, and heat capacity. And then probably most important is the last category, transport properties. Viscosity, conductivity, diffusivity, and transference are all very key toward assessing the transport capability of an electrolyte within a cell. Okay, next. And here's the reports generated with each run. Each report has distinct set of properties that it contains, and so you can go directly there and find what I would consider to be a genomic level report on different electrolyte properties. Okay. Currently, the library has 63 solvents and nearly 40 salts. And within this range of compounds, we have things like carbonates, linear and cyclic carbonates. We have esters, ethers, nitriles, We have some phosphorus containing compounds like phosphozines and phosphates. And then we have some sulfur containing compounds as well. Recently, we've been adding more compounds like BTFE and TTE that are used for localized, highly concentrated electrolytes as targeted for lithium metal type cells. Okay, next. This slide helps to point out the complexity of predicting some of these properties. And so this is the diagram that is at the basis of electrolyte conductivity predictions through AEM, seeing how complex and interconnected these terms are. So electrolyte conductivity has a molecular basis starting with ion solvation. Through ion solvation, we get things like the effective solvated ionic radii. And then through some permittivity and ionic charge type information, we can assess the ion association through ion pairs, triple ions, and solid solvates. The reason why that's important is as you have the occurrence of ion pairs, for example, those ion pairs are then withdrawn from the population of charge carriers. So you want to minimize ion pairing if you can to allow as many current carriers to be present in solution. Also, we have electrolyte viscosity, which is a very important term that affects electrolyte conductivity. And then random ionic motion can also be seen as a contributor. As you increase temperature, the random ionic motion tends to increase its contribution toward reducing conductivity. And then things like dielectric drag and different effects from the relative permittivity of the solution, these also have an impact on the movement of ions and the measured electrolyte conductivity. Okay, next. And this slide provides a quick set of examples for AEM validation. On the upper left, we have a couple of plots that have diffusivity data. The data points are the black circles, and these were obtained through post-field gradient NMR. The blue curves are AEM predictions. So between the PC LITFSI system and the gamma butyrylactone LIBF4, we have some very close agreement between model and measurements. On the right-hand upper set of plots, we have conductivity measurements in the data points, and then the curves are the AEM predictions. This information was gotten through a collaboration with Jeff Don's group at Dalhousie University, and they were looking at EC and DMC as kind of the starting solvents within electrolytes, and then adding methyl acetate at different amounts to see the effects on conductivity. So it was a very good collaboration with that group, and we see good close agreement between modeling and the data. Lower right, we have some similar plots for conductivity, but looking at EC-EMC with LiPF6 at different formulations, different temperatures, and over salt concentration. And then lower left, we have the some viscosity plots that are for carbonate mix with LiPF6. Basically looking at temperature effects going from 80 degrees C down to -20, and the model fidelity remains high across that whole range. Okay, next. Thought it was worthwhile to mention diffusivity because it figures centrally into the effective transport within an electrolyte as used in a cell. So it's a very proper metric to be looking at as a screening term. So diffusivity is also used in Newman modeling as a kind of a cornerstone metric for assigning the efficiency of transport. In these plots, we have a couple different ways to look at diffusivity. If you look at the equations on the lower left, the top one has the salt diffusivity. It's given by a Nernst stoichiometric average. That's been used for decades, but recently, I'd say recently in the last few few decades, John Newman has developed what's called a thermodynamic factor, which helps to account for the more concentrated salt effects in solution. And so a lot of practitioners of the Newman modeling will want to use the thermodynamic factor within their what they call apparent diffusivity calculations. So on the left-hand side of the plots is the Nernst version of the diffusivities for different electrolytes at different temperatures. Black being 20 degrees, red is 20. I'm sorry, black is 0 degrees, red is 20, and then green is 40 degrees. And then on the right-hand side, we have the apparent diffusivities, looking at some different electrolytes at different temperatures as well. So brings a lot of, I'd say, fidelity into the electrolyte property space when these kinds of tools can be used, and it makes them more compatible with complementary tools like the Newman model. Okay, next. And now we have more molecular scale type properties that AEM provides. And in this case, we're looking at lithium desolvation and the process that's behind that. So if you start with a lithium that's fully solvated, such as the one given kind of on the left-hand side of this process, in this case, it has 4 solvents around it. Depending on the electrolyte you choose, that could certainly vary, but this is just for demonstration. As it moves from that spot, kind of in the bulk electrolyte and over toward the right, where it's going to be inserted into some form of an electrode surface, it has to shed those solvators. So each solvator has its own price tag for being removed and breaking that electrostatic association with lithium. As you go toward the right, the standoff distance between solvent dipole and lithium becomes lesser, but they get closer together. So the binding energy that has to be broken becomes higher. So between the first solvent and the last solvent is an increase of cost of binding energy to desolvate the lithium, and an increase in the related desolvation time. Okay, next. Here's some examples of that process and looking at how that actually looks for choices of different electrolytes. I'm going to focus probably mostly on the upper right-hand plot here, where we have the net ligand-wise lithium desolvation energy versus salt concentration at 30 degrees for 4 different electrolytes. Our baseline system is the red curve, and that's EC, EMC, LiPF6. The other 3 electrolytes are highly concentrated electrolytes, generally between, well, they range between, in practice, when we use them in cells, they range between like generally 2.5 to 3.5 molal. So we wanted to see what their behavior is for a large range of concentration. But now we're looking at the ligand-wise desolvation energy, which is relevant more toward the anode if we were doing something like a fast charge. So in that case, we would be wanting to look at kind of the lower end of the concentration scale. And within that range, we see one candidate in the light blue curve provides a reduction of the desolvation energy by about 10 to 15% compared to the other systems. And so that is a very clear indicator that that system is actually a good candidate for fast charging. And when we built some coin cells and did some EIS measurements based on the interfacial attributes of the Nyquist plots, it corresponded very closely to this 10 to 15% reduction. So we're seeing some good correlation between the pre-screening provided by AEM and what we're actually measuring and capturing in our cell data. Okay, next slide. And this is just a quick snapshot of some thermophysical properties predicted by the model. On the left, we have some thermal conductivity profiles for a number of different electrolytes envisioned for highly concentrated electrolytes for fast charge. In the middle, we have some relative molal enthalpy, which is also called heat of dissolution. And then on the right-hand side, we have the excess heat capacity, which is the change in heat capacity as you add salt. And so these terms, again, can be used for assisting with thermal management design for different batteries and understanding what the materials cost are for maintaining particular metrics of temperature control as you use these batteries, electrolytes in the system. Okay, next. And then for those of you who are practitioners of the Newman model, the AEM does provide some clear terms that are usable within the model. Those are listed on the left-hand side here. Molar salt concentration, activity coefficient, specific ion conductivity, salt diffusivity, transference number, solution density may appear in some versions of the Newman model, and then the thermodynamic factor. So these are a lot of times the practitioners that use AEM with the Newman model are able to develop very precise ways of extracting these terms out of the AEM outputs by doing like an interpolative technique where they can, look at very, very particular concentration values as concentration polarization develops during the simulation of the Newman model. They've told me that has increased their model accuracy tremendously. So it's good to hear that AEM can have an impact on a tool like that. Okay, can we go to the next slide now? I think the last example here is to show how we've used the model to support fast charging goals within our DOE program. We have the Department of Energy has a fast charge program called Excel that has been looking at trying to develop fast charge batteries that can do a 10-minute charge and still maintain roughly 70 to 80% of charge capability, but have thicker electrodes. So we're pushing past 100 micron thick laminates now within our anode and cathode systems with these cells, and the AEM assisted electrolytes are still doing quite nicely with that. Next slide. This shows what we typically look for when we're running the code and then getting the information out for the fast charge electrolytes. We want, of course, to have lowered viscosity. The black here is our baseline. Then these other systems are candidates for fast charging. Again, these are envisioned to be used at higher concentrations. So even at higher concentrations, then the baseline would typically be used around 1 molal. If we go to 3 molal, we still have very competitive viscosity. The same happens with conductivity, where the maximum value that we see for these systems is quite a bit higher than the baseline, and then the range of usable conductivity out, say at 10 millisiemens per centimeter, is still very competitive, and it remains high, even up to like 3 molal or so. It doesn't become constrained. Similarly, we see high salt diffusivity that persists in comparison to our baseline. And then this lithium desolvation energy is similar to what we saw before, showing improvement over the baseline for this particular system here. So in concert, we use this type of information to screen out candidates, and then we use them in cells and validate our choice. Okay, next. All right, so you saw that the current library has a little over 60 solvents and about 40 salts, but you might wonder, what about compounds not found in the library? Uh, so it's a very valid question, and it's something that we've found a very clear answer to. We now provide a way to include user-defined, arbitrarily chosen chemical compounds, or ACCC, and these can be solvents or salts. ACCC compounds can be mixed with library compounds in the formulations, so that basically when you input the parameters for each ACCC, it's as if it resides in the library and is used in a very similar way as the code runs. So in this way, literally so many thousands, if not millions, of compound options are made available as long as the user is providing the correct type of input information that is allowed for within the code. And there's a couple ways to do that. Let's see, is it in the next slide? Let's see. Not quite, okay. So the ACCC bypasses the AEM library. If you look here kind of toward the bottom. So as it does that, it inserts the information at the right point, kind of in the middle of this slide, as if it just came from the library, and then it's used in the calculational architecture within AEM. Okay, next slide. Right, so in order to utilize this new capability for solvents and salts for AEM, a user needs to provide estimates for the different ACCC parameters. And we have some screen captures here in the next few slides. These terms can be input through a table that's within the GUI version provided by Ridgetop Group, or they can be read through a string text file during command line interface program operation. Either way, it works the same, basically. It's just how the information gets to the code. Many of these ACCC parameters are known in the published literature. It can be found in different compilations, and perhaps easily derived. And in some cases, if you kind of have a sense for a class of compounds that you've already gotten information for, be it carbonates or esters or nitriles, you can use some of that known information to provide initial estimates for the new ACCC compounds if they are unknown at that point. Okay. So next slide. Yep. So there's different types of information that goes in. Basically, you're looking at what information is housed in the library. So now the user is asked to provide this type of information. At the top here, we have some very typical stuff, shouldn't be hard to find. So molecular weights, densities, viscosities, dielectric constant, or relative permittivity at room temperature. Those kinds of things are low-hanging fruit to find for all kinds of compounds. If you don't know them, then we can arrange to use some structure function relationships to make estimates for those. In the middle part there in red, we have some other probably more fine-tuned information, things like refractive index, dipole moment, some solvatochromic type parameters, such as pi star, and then the Reichert's normalized polarity index. These things kind of hearken to the propensity of a solvent to be occupying space near a ionic species. So this is important to start looking at ion solvation types of tendencies between solvents and salts. And that's how these particular terms function within AEM. Then as we go further down, we get more into specific interaction parameters that allow us to see the time spent, the residence time spent between a solvent and an ion in a solvation shell, and also the ligand, the reference ligand length between that interaction. So we got the time spent, we got the ligand length reference, and then at the bottom we have some additional information that's needed to look at things like surface tension. So that's a mouthful, but I think you'll understand and agree that in order to get the accuracy out from AEM, this level of information is needed to feed the models to allow that accuracy to be expressed. Okay, next. And then we have analogous terms that if you choose to put an ACCC salt into the simulation, these are what those terms look like. It's a little bit of a shorter list, and there's some common items with what you just saw on the solvent side, because if you input a salt ACCC, the code needs to know what solvents you're using with that. So as this is done, the salts are able to be used equally as well as the solvent class. Next. And then this slide and the following just shows some validation of using these choices of solvents and salts either through the library, and that's the black, or as an ACCC, and that's the red dashed. So these results are basically indistinguishable, meaning that we've done a good job in allowing the ACCC route to be equivalent with the library-based route. So that's these are basically single salt and single solvent. And I think the next slide has some more complicated cases. Next slide. There we go. So at the bottom there, we see some multi-solvent cases where the accuracy remains very high. Basically, at least 99% agreement with the library-based approach for getting that information. Okay, next. I think we have a demonstration from Ridgetop, so let's go ahead and do that.
Yep, excellent. Yeah, thank you, Kevin. All right, so let's see if I can get in. All right, can you see my screen okay still, Kevin?
Yes.
Perfect. Yeah, so for today's software demonstration, we'll really kind of cover 5 key features that we've been working on based on the customer feedback over the last several months. So this includes things like parsing and displaying the results from the 20 different data output reports generated with each AEM simulation run, and then running simulations in parallel, appending multiple simulation runs together into single reports, and then exporting data outputs for CSV files, and then completing the ACCC integration and capabilities. So we'll run an example simulation here shortly, but just to kind of touch on the ACCC capability that Kevin just covered, you can see with this new version of the software, you can now create your own material properties for the compound library. So whether it's a salt or solvent, we have a framework that allows that to be included into the library and expanded for customers. So oftentimes when you're doing new material property design or new battery design and development, the electrolytes and additives are the proprietary part of a particular design. So how can these be optimized for certain programs or initiatives is really up to the battery design engineers or electrolyte development teams, that we've had the privilege of working with across the globe. So Thankfully, this capability has been robustly tested and proven with many of the compounds that are in the library where we've had data for this to validate the solvents and salts that are by default in the material property database. So we can see that here and again for the salts as well. So the input parameters and the ability to customize these parameters is very useful for having an iterative process to um, adjust the model accuracy or calibrate the model for a particular compound. So here we'll start out by importing a previously built example with example 1 and example 2. So this is a very useful capability where we can now run multiple simulations in parallel. So I'll just run examples 1 through 3 here pretty quickly. And they're preloaded here. So I think example 2 takes a little bit longer, but example 1 already finished. And then here's example 3 that'll be running. So up here in the upper right, we have the examples that are being run and whether or not there's a timestamp being kind of appended for each of these. So as they go through that process, we'll get kind of a check mark when they're complete, but we still have access to the rest of the simulation and its capabilities. So if we go to example 1 and some of the results here, we could see this was for a 3-solvent, 1-salt mixture with EP, DMC, EC, and then LiPF6. And here we can see example 2 just completed. And then the max total salt concentration was 5 mol. The temperature range was from -30°C to 60°C in 5-degree step sizes. And then we use some of the default parameters for ion stability, contact angle, total pore length, and the salt concentration of interest. So as we can see, there's 20 different reports here in addition to the TXT file housing the example 1 simulation parameters. So these are stored in a timestamp directory that if you want to take a look at them in a file explorer, they're shown here. Or if we want to look at the preview of these results, we can actually see that here in the software capability. So if we want to look at a particular plot of interest, maybe we want to look at the viscosity or ionic conductivity, we can filter, that by the temperature range, the salt composition, solvent composition for this particular simulation. So this is very useful when looking at several different temperature ranges or different simulation results. So if we're looking at the diffusivity or the specific conductivity, we can now kind of preview or zoom in on certain parameters as well, which is a very, very useful capability. And then exporting those to a CSV file. So if we want to, maybe store this for export in another tool, we can do that here. Go to that program directory and then take a look at it. Yeah, maybe Excel or so. Very, very useful capability for additional analysis and comparison or report generation. And then in each of the reports, there's a lot of different information. So report 1 has kind of just a summary of the key property metrics. But, if we're looking at a larger simulation, these could be very large in size. So there's several data tables in here that we're able to automatically parse and display and do some initial analysis and comparison for the simulation conditions of interest. So we have a few other capabilities here in the software, that we're working on. Things that would include for the traditional command line interface would be a set of Python scripts and documentation for running iterative simulations through the CLI. So that's another capability that the team is currently working on. And we're also working on adding additional comparison and analysis capabilities for specific plots of interest. So if you want to compare multiple simulation runs under different conditions, we're going to be adding that capability, as well as the ability to upload your own lab or testing data or experimental data to see how that compares with your simulation results. So lots of areas for collaboration with our existing customers as well as new customers that have expressed an interest in using the tool for their battery R&D initiatives. All right, so yeah, I think example 3 here is still running. I believe that one's the optimization run here. So that will run for some time, but it'll just do that in the background. Try to get back to that slide here. So we'll be sharing these slides with the registered attendees as well as, uploading a version of this webinar on our YouTube channel. So in summary for the software demonstration, you can see some of the example inputs for example 1 shown here, the output report for report 1 for the summary of key properties, and then some data plots that were previewed for the specific conductivity. So some of our existing customer segments that we're working with are with battery manufacturers and researchers, as well as new material property developers for batteries for EV applications or grid energy storage applications. We've done a lot of work in the robotic industry, and we've also worked closely with Department of Energy, either through the SBIR program or through some of Kevin's work, with the fast charge program or long duration energy storage programs. So the software today is available through annual and term-based software license agreements or SLAs. So typically we have a 2-tier pricing model for commercial and academic organizations. And we're happy to provide quotes for anybody that is interested in, utilizing the tool, whether it be for academic research or commercial development of a new material property. And there's also opportunities to bundle the software with other complementary tools such as SalSage and A-Rule, which we have been working on with Kevin for several years. So in conclusion, the AEM software and ACCC capability really opens up the door to expand the library of new compounds and possibilities that can be utilized for battery R&D, but the software is also extendable to other applications as well. So Kevin, I don't know if you maybe want to touch on some of those other applications, where we've seen interest in utilizing AEM, or if you have any additional kind of closing remarks for the ACCC module today.
Well, the interest for using AEM in general for batteries it ranges all over the spectrum. So DOE just put out an FOA call for sodium ion systems. So now we're looking at aligning AEM capabilities with supporting that consortium. And also we're supporting silicon type cell chemistries. We've talked about supporting lithium sulfur type systems as well, because they have a unique set of considerations and concern with sulfides that can be developed and basically affect and turn off the transport of lithium within those particular cells. And lithium metal, of course, is very important. That's why we've had some recent additions of compounds that will help support that. I would also say that as we have more users that are participating in using the ACCC capability, that we're going to encourage cooperation between users to share those property sets, so that if they feel like that's something that they can do without, violating a proprietary nature of their work, then we want users to be able to exchange that information and just help expand that knowledge more quickly.
Yeah, absolutely. Absolutely. Yeah, so I think this is a great transition here into our Q&A discussion. So we'd like to thank everybody for their participation and watching today's webinar. But if there are any, immediate questions or concerns, we're happy to take those at this time.